in this class, except for exams. Exams are one-off. But if you miss anything in this class, each type of assessment, you get 2 retakes, right? So the pre-lecture stuff, the participation activities, if you miss any, send me an email and you can have up to 2 retakes without any questions asked. Same with the challenge activities, 2 retakes, no questions asked. Same with the labs. If you miss submission of a lab, 2 retakes. No questions asked, just request it. I'll take note that you've used up one of your 2 or 2 of your 2. I would rather you do the work rather than miss it. So I used to, years ago, I used to have no due dates on anything. And what I found out happened then is at the end of semester, I had 1,000 things to mark because nobody handed anything in until the end of semester. Because that's no good, because you don't get feedback in the moment, and it just doesn't work. So that's where we are, and Lab 4 and Lab 5 are the main things on the bill today, but I want to talk a little bit because Lab 4 and Lab 5, you need to do a proper lab report. Some of you have sort of already been doing it with a Microsoft Word file and a cover sheet, and that's okay. Hasn't been necessary until Lab 4 and Lab 5. So you'll be glad to know and ask that because my computer decided to do an update when I turned it on this morning, I've been talking for maybe 2 minutes. So
Yeah, the I-91 is a parking lot today.
Yeah.
There's some kind of big accident.
Oh really? Yeah, that's no good. So I'm just really starting now. So there's a couple of things I want to talk about today. I may talk a little bit about adders, but only in passing. The main piece on this list is representing data and data types. I need to talk a little bit more about that to help you do Lab 5. Okay. And just a reminder, they're the things that have to happen. And the next thing, by next week, this time next week, I will have released the midterm exam. Okay? The way I do midterms and finals is you have to book a time with me to do it online, and I release all of the questions except maybe some details in the question, but I release all of the questions at least a week, hopefully 2 weeks before you have to do it. Right, so there's no surprises. Don't think that means you don't need to study. I have had people have the exam paper in front of them for 3 weeks, and then when they get to the exam, say there's 5 questions on the exam, they have passed, that is, not given any answer, P-A-S-S-E-D, passed as in not given an answer, on 3 of the 5 questions. They failed. They gave an answer, but it wasn't worth more than 50%, if that. So be aware of that coming up. And the same thing with the final. Again, oral. That means it'll probably be during finals week, although I'm happy to arrange at other times. Some people have other stuff happening at the end of the year and need to get out earlier or get out later or what have you. But we can talk about that at the end of semester. So it's just a reminder for me to publish the midterm, and we'll talk about that next week. So I've been putting out some project ideas, and I don't know if any of you have ever seen the fencing reaction timer that Professor Broderick and others put together. It was a big construction with 7-segment displays on it and a big target pad, and the idea was, and an LED, and the idea was that when the LED flashes, you have to use your foil or saber or whatever, your fencing stick, to stab the button, and it would test your reaction time. So the aim here is not so much to build the whole structure, but just to put a reaction timer into here. So when the timer flashes the LEDs, you've got to close one of the push buttons as quickly as possible, and then the 7-segment display shows the reaction time in milliseconds. Right. And maybe an addition would be, instead of flashing LEDs as the signal, maybe you make the buzzer buzz as a prompt, or maybe both. Okay. So I think that might be a fun one to do, just to show what you can do with this board. So the things I want to talk about today, most of today is going to be about the labs. And to help you do the labs, I need to talk about representing data. I do want to briefly mention adders. And then we want to finish off lab 4 and deploy lab 3 to the board, and maybe do a test bench for it as well. So before I go into that, let me talk about the labs. Let's go with that one. So remember, I've said the sequence before, but what you have to do with the lab reports is to say what you planned, say what you did, and then discuss the results, right? And for the plan in this class is the design, right? So truth table to logic circuit, either circuit or algebra formula. Okay, so how do you go from the statement of the problem, build a half adder, to what the actual thing you have to do is? And then the do part is either multisim or VHDL. Okay. And now that we've talked a little bit about test benches, the review part, at least for the VHDL, is to display the result of the test bench, or display the test bench, but then display the result of the test bench. Okay, so that's the aim. And let's just see if I can go back here. Remember my notes about lab reports. Now this is way more extensive than you will have to do, but please have a read through this to see what I'm looking for in your lab reports. Let's just see if we can. I probably should update this, maybe add a few more examples for the classes I'm teaching for CET 236 and for this class where it requires labs. But it's the key pieces for each section are in the boxes at the end of each section. Right? So why should I keep reading? What's the background information that the reader needs to know to read the rest of the report? The procedure. How can I reproduce what's in here? What are the results? What's the outcome? The discussion. What went wrong? What went right? What did you learn? And then conclusions. What do you want the reader to take away? Sometimes, what is the writer going to do next? What do you plan on doing next? And probably for lab 4 it's lab 5, and for lab 5 it's lab 6. But once you get to lab 8, then maybe you can talk about what you want to do in your project. So let's just quickly also have a look at the rubric for the lab reports. I think they're set up. I hope they're set up. Clicked the wrong one. So you should be able to see this if you click on that. Right? So this one, let's make it a bit bigger so we can read it. Okay, so this one, I need to see that the VHDL compiles. I need to see that the VHDL implements a full adder and a full bit adder. I need to see that the multisim implements a full adder and full bit adder. I want to see that naming and formatting and everything is good. And I want to see that the test bench verifies correctness. Now, for lab 4, you have two pieces. You have the full adder and you have the 4-bit adder. that probably means your test bench, it means you need 2 test benches, one to test the full adder and one to test the 4-bit adder, or your one test bench tests both components. Okay? Remember, when you set up the test bench, it usually only focuses on one component and it gives you only one component in there. Okay, so this is it doesn't talk about the introduction, so maybe I need to update this, but this is specifically what I'm looking for lab 4. So let's go back to the notes. Okay. So your lab report should have the design part, should have screenshots of the multisim and maybe screenshots of the VHDL, although VHDL I tend to want to see the actual code, which doesn't necessarily go so well with screenshots. The nice thing about screenshots in VHDL is you get all the keyword highlighting in Quartus. So that will work. Just make sure it's just the code rather than the whole thing in Quartus. Okay. So there's just a reminder on the screen of what the lab was about. Let's just make that full screen. Right, so there's our full adder. And then the actual thing we're implementing. Oops. Why does it do that? The actual thing we're implementing is 4 full adders and then an add or subtract. I call this a subtract input, right? So if k is 0, we just have a 4-bit adder. But if k is 1, then the B input is first of all complemented, so that's what those exclusive ORs are doing, complementing each bit in B, and then we're adding 1, right? Because that subtract bit is going into the carry in on the first full adder. And that complement plus 1 is 2's complement way of negating B. So we turn an adder, a 4-bit adder, into a 4-bit subtractor. What's happening? It's not doing anything. Okay. So there's a few things that we need to talk about, and I wasn't quite sure what the right order is, so I probably got it in the wrong order. So let's start with the for loops. Now, in your test bench, I've asked you to exhaustively test the 4-bit adder subtractor. Right? Now that means we've got 4 bits of A, 4 bits of B, and that K input. So that's a total of 9 bits. If we exhaustively test 9 bits, that's 2 to the 9 possibilities of different inputs. Putting in 512, because that's what 2 to the 9 is, putting in 512 different examples in your test bench is going to be painful. So my suggestion was to use for loops like this to iterate through all possible values of A, iterate through all possible values of B, and change the subtract input to its two possible values. Now these three for loops are doing slightly different things. The first two are doing basically the same thing. And when you've got a for loop like this in VHDL, this variable A in, or in fact the variable B in, are typed as integers. That means they are of integer. The values they can have are integers. This loop here is doing something different. Here, the subtract bit, I've decided I need it to be in our standard logic type. So I've effectively set the type of subtract to be standard logic. And then I can explicitly say what values. Remember, standard logic has other values. It has X, it has H, it has L, Z. There's another one, W for week, right? But I just wanted to take on these two values. So now instead of having, remember our the test bench I did before. Remember the first line of the test bench I had was we set A in to be 0, 0, 0, 0. Right? We set B in to be 0, 0, 0, 0. And then we set subtract to be 0, and then we assert that S equals 0, 0, 0, 0 with report if it doesn't. And then the severity error, and then assert on the value of C out, and that's going to be 0 report, etc. That test, 5 lines of test, would then have to be repeated another 511 times if I were going to exhaustively test every option. I'd have to first of all change A in to be 1, then 2, then 3, all the way up to 15, 4 ones. Then I'd have to change B in, and then I'd have to do the whole thing again, but with subtract equal to 1. And that is inherently error prone. Whereas if I do it this way and just have an appropriate test inside the innermost nested loop, then I should be able to test everything. The other subject I want to talk about quickly is related to the difference between integer and standard logic. Something we often want to do in a strongly typed language like VHDL is convert from a value in one type to a value in a different type. Everybody okay with for loops before I move on? Right, and I should have put up here that there's several end loops, end space loop that should be. Right, one for here, one for here, and one for here. And then the thing in the middle there, right, any statements inside here are executed 512 times. Okay, so that's the other piece I wanted to talk about. So far we've talked about the one part of the IEEE library that gives us the std logic and std logic vector types. But there's another piece of it called numeric std, standard numerics. And the main thing that gives us, that I want to talk about today, is the ability to convert between different types. Right? So we can convert from signed to unsigned using to unsigned, and we can convert from integer to std logic vector using the std logic vector conversion. I think it's a macro, but anyway, call it a function. Okay, the way that works, this might be a bit hard to read, unfortunately, but the to unsigned piece takes as input an integer and also takes in how many bits it has to output, right? Because an unsigned number is a binary number, and the nice thing about VHDL is you can effectively determine arbitrarily sized binary numbers. In our example here, it's two 4-bit binary numbers. But it doesn't have to be just 4. It could be 512. It could be 1024 bits if you really wanted. So you've got to tell to unsigned or to signed. Remember, binary numbers can either be unsigned, in which case they range from, if there are n bits, they range from 0 to 2 to the n minus 1. If they're signed, then 1 bit of that is taken up with the sign bit. So then you can only go from about minus 2 to the n minus 1, the whole n minus 1 is the power, to plus 2 to the n minus 1. Right? So you've got to give to unsigned and to signed the length, how long the item is, and you do that by using a single quote and the length of the keyword length, right? So for output 1A, it's 4 bits long, and so the value of this length will be 4. The nice thing about that is you don't have to, if you hard coded this to 4, and then later on you decided you needed to change the length of the output to 6 bits, then you'd have to go down here and say, oh, is that 4 right, or should it be 5 or 6 or 7 or 8? Whereas here, you don't have a hard-coded number. One of my pet peeves in coding generally is the use of magic numbers. And I'll point out here that I would call these magic numbers. And so the question then is, I decide I'm going to change output 1A to be 5 bits long. So I change that 3 to a 4, and I make it 5 bits long. If I just use magic numbers, I don't know whether there's an assumption of output 1A and output 1B being the same length. Right? So then I've got to really think hard, and do I need to change this 3 to a 4 as well? There is a mechanism which we haven't covered yet, and so I'm not looking for this now. There's a mechanism to allow you to put a name in here, another variable. It's called a generic. In other languages it must be called a constant. In VHDL it's called a generic. Okay. And the nice thing about using a name in here is if you use the same name, then it's very clear that those two numbers should be the same. Whereas if you just use a magic number, it's not necessarily clear whether they should be the same. I do tend to be okay with 0 not being a magic number, because 0 is 0. I also, tend to be okay with things like true and false. They're already pretty clear. But most other numbers, you should use a symbol instead of the number, and use a constant or a generic. Okay. So I decided to have a look at that. There it is. I decided to have a look at how to do the how to do the test bench for lab 4. And this is the test bench. Let me just make it maybe a little bigger. And so you all know that the first piece is just bump, because it's what Intel does at the beginning. And you can see I generated it on the 18th, which was last week. And then the interesting part starts at the library, right? And now I'm starting to use that numeric std part of the IEEE library. So then this is the test bench, right? So the entity statement for the test bench has no inputs and no outputs, so there's no port statement. Okay, but it still needs an entity statement. And then the architecture starts, and there's the name of the architecture. Right, let's just, now that we're in here, we should be able to do that. So there's the name of the architecture. Right, and it's of type whatever the entity was. Right, so there's the name of the entity, so that has to go here. Now there's lots of other pieces that are part of the architecture definition that don't actually implement any logic, right? And one of the first pieces, and it puts the name in, which is kind of nice. There's constants, right? So what I was just talking about before, they're called generics, could be called constants as well. If you were defining the bit size, 3 bits or 4 bits, you would probably put the definition for that in that section immediately after the line that I've highlighted in green. We haven't got to the begin statement. Remember, the actual logic in an architecture starts after the begin statement. So the other thing you can see here, the next thing, are signals. And we do have some signals. Right? There's signal A, B, C in, C out, and S. That's another thing. If you need a temporary variable inside what you're doing, inside the architecture, you define that temporary variable, that signal, up here, right? So that it can be used. And here we've got A, B, C in. They're the inputs to our 4-bit adder. And we've got C out and S, which are going to be the outputs. The next thing that happens, another thing that can happen before we get to the begin statement, is we can define some components. It might be that we're doing something really complicated inside this architecture that we need submodules for. We need separate components. And that's the case here. Here this is a wrapper around a test harness around a 4-bit adder. So at very least, we need a 4-bit adder component to be available. Now, 2 things need to happen with the component statement. The first thing is that you need to use the right name, right? The name of the entity that you're going to use. So where we've defined the 4-bit adder in the VHD file in the 4-bit adder, it has to match exactly the name 4_bit_adder. The other thing that has to match the entity statement is the port statement. So I recommend just cutting and, if you weren't using the template writer to generate this, when you need to make your own components, I recommend just cutting and pasting the port statement from the entity declaration. That way you'll know it's correct. Okay, and then we have the end of the component. And now finally, I don't know, we'll go with that one. The light blue. Finally, we have the begin statement of the architecture. So here is the start of the implementation. And then the way the template writer in Quartus works is the first thing it decides to do is it decides to instantiate the component under test. Right, so this statement is saying I'm going to create a 4-bit adder. I'm going to call that 4-bit adder I1, and the way I'm going to access that component is its inputs and outputs are going to talk to these signals that I defined up above. Okay? And I always forget which way round it is. You'll notice it is a bit confusing because it just says A goes to A, B goes to B, C in goes to C. But one side is the name of the port, the other side is the name of the signal. Let's just see if we can let's just see if we can find a quick explanation. I think page not found, that's no good. Okay, so maybe you can't see this. Let me see if I can. There we go. Ooh, that's a bit too much. Okay. So here we first of all have an AND gate as our component. It's got inputs of X and Y and it has an output of Z. And they've used the shortcut notation, right, for the defining an instance of the AND gate. They've got the name A1, they have AND gate, and they have the port map statement. And then the things that they put in there are the signals, right, that go to X, Y, Z. If you're making it explicit, then this would be the definition, right? So the signal is on the left-hand side and the port is on the right-hand side, right? So A is our signal. It goes to X, which was the first parameter. B goes to Y, it's the second, and out goes to Z. I recommend, you can see, I think they made a mistake in defining out as the name of the output. You can see why, because the thing that produced this has found it to be a keyword. And out is a keyword in VHDL. I would recommend against using variable names which are keywords. Right, that's why it's been highlighted. It shouldn't be highlighted. It's not a keyword. It's not being used as a keyword in this instance. Okay, so just a reminder, the left-hand thing is the signal and the right-hand thing is the port. So these are the signals and this side is the port. So all of these right, all of this side has to match these, right, because that's the port. Those names, the grey highlighted names, have to match. Okay, so now we've got a thing to test. It's called I1. And the way the test bench goes is it splits the test into two components, two parts. The first part is a process that initializes everything. And because it doesn't know, the template writer doesn't know what you're going to test or what extra variables you might need or signals you might need, it doesn't put anything in there. But you can see it's labeled init and it says there's code executes only once. Now there's lots of things I haven't told you about processes. Can anybody give me one thing I have told you about processes? Let me see if I can bring up my app and pick on someone. Here we go. David, can you tell us one thing that I have told you about processes? I think there's only one thing I've told you about processes. No? No? Okay, let me try someone else. Michael.
No idea, but I have that's code that executes only once.
Yeah, you're reading it, not quite. I was hopeful with the way you started that, but so it's Michael F. No? Matt, any?
I got nothing.
Get nothing. So remember, one of the things I told you about VHDL is that everything executes at once, right? The whole thing happens at once. The place where that is not true is inside a process statement. A process executes sequentially, right? Remember the I don't know if you remember the code for the half adder, right? We just had 2 lines in there, and it didn't matter what order you put those lines in, they were always going to execute at the same time, right? There was no process statement in that half adder. It's a really simple device. But here, as it says, as Michael P could read, the code executes only once, right? But it executes sequentially, right?
Executes as traditional code.
Sorry?
It executes like traditional code, let's say.
Yeah, exactly. It works very similar to C or Java or C++ or C# or Python or anything like that, right?
So how does it execute all at once? Does it go through like the compiler?
Because executing all at once, it's not, that code is not actually executed, right? It's connecting the compiler once it's deployed to the FPGA. The compiler is just wiring things up, right? So it wires up this input to that output through this logic gate. And that's something I need to talk about, is how does the FPGA do that? We haven't talked about the detail. But there are lots and lots of little logic gates, or they're actually a bit more complicated than that, but that are reconfigurable so that it's not code that's executing when everything's happening in parallel. It's just that the connections are already made, so it just happens. It's different inside a process. Now we have to have a little compute engine built up, and again the FPGA has little effective compute engines in there to be able to do that. So that's a good point. I should probably, I don't think I'll be able to do it today, but next week I'll talk about the internals of the FPGA. To see how you get that distinction between the everything happening at once and the sequential. Okay, good question. Thank you. Okay, so I'm just going to rattle off a few other things that I haven't told you yet about process statements. This process statement, and you can see it's sort of mentioned here. This process statement doesn't have what's called a sensitivity list, because there's the question, if you've got this list of things that has to happen, when does that happen? Right? And a sensitivity list tells the process, if there's a list of variables there, or a list of signals, that tells the process, if any of these signals go high, execute this process. Right? If the process is already being executed, that won't happen. But if the process is not being executed, and one of these sensitivity list variables changes, then the process executes. The init process has a wait statement. Right? You can think of the wait statement by itself, just like that, with no other variables, as a halt, as a stop. That's why, oops, so that one there is like a stop. That's why this can say code executes only once. Well, there's two things. One, there's no sensitivity list, so the process just happens, regardless. It executes only once because after it started executing, when it gets to the wait statement, it just sits there. Doesn't do anything more. Okay? Now, there are other uses of the wait statement. You can use the wait statement to simply delay execution. Right? So you can say, instead of just wait, which is stop, you can say wait for 1 microsecond. It's a US, or MS, or NS, right? You can say S if you want to wait for a second. Right? So those are, that means that there's a slight delay before anything else happens within this process, if that was the wait statement. If we had this wait statement instead of this wait statement, and the process was exactly as it is there, as soon as that wait statement is executed, the process would restart, and then the process would restart, and then the process would restart, right? Because there's no sensitivity list, there's no other code, so the only thing that would happen is you would get this 1 microsecond delay every time. If you had other code in there, then that code would execute, then you'd wait, and then the whole thing would start again. Okay. Now, tests in the test bench are usually put, let's go with that green, are usually put in the always process. Right? That's why there are 2 processes. There's an initial one, initialization one, and there's this one which actually does the test. And it does say there's an optional sensitivity list. So if, for example, I had always process A as the statement, then this process would only execute if A were high, right? Or rather, if A changed. But as it is, if this process executes and there's nothing at the bottom, we'll see there is something at the bottom, it'll keep executing after it's finished one run through. Now I've defined some variables here. Now variables are different from signals. Not too different, but they are different. A signal is something that will probably end up being on a wire, right? It's an externally viewable value. A variable is something that we want to have available to make our code readable, but the compiler can get rid of it as far as making it a voltage we can measure. So here I have 3. I have one called 6 bits, which was just a temporary variable I needed, and it's a static logic vector of 6 bits. There's a counter variable, errors. It's a type integer. Because this is a test bench and I'm automating lots of tests, I wanted to count the number of errors that it finds. So I decided, note in all 3 of these there's colon equals. Variable assignments are different from signal assignments. Variable assignments use that instead of that. Right? So that's happened. And then the third variable, I hope you're confused by the lab 4, because I got confused by what lab 4 should be producing. So I decided that I wanted to, particularly for the, I understood what was happening with the sum output, is either the addition or subtraction, but I got confused by what I thought I was seeing on the carry out. So I decided to calculate what the expected carry out of the 4-bit adder should be. So that's what that variable is for. Okay, and then we've got our, let's go with another colour. Right, then we've got our 3 for loops that I had earlier in the lecture. And you can see there's lots of stuff happening. And then the end of the 3 for loops. And you'll notice I decided that I wanted to say what the result of the test was. Because the first time I ran it, I didn't have that. And I hit run, and nothing happened. For the first time, I didn't get any errors. And I didn't have any indication, though, that it had actually run. So I put this in here to say, yes, it ran, and it got 0 errors. Normally, previously I've only used the report statement in conjunction with the assert statement, right? But here it's just like a print statement, right? Or Brightline or whatever language used, printf if it's C. The other thing I will note is VHDL is a strongly typed language. So everything has to be the same type. So this errors is an integer. This test completed with is a string. So I need to convert that integer to a string so I can do concatenation. That's like a string concatenation or addition. I'm putting one string up against the other string. That's what the ampersand is here and here. Okay? So there I can report out the errors. Okay, let's go back and see what's actually happening. In the loop. Right, the first thing I have to do is I have to take my loop variables and convert them into signals. Right, so I take my A in and I convert it into my A signal. I take my B in, I converted that to convert that to my B signal. I take my subtract and I say that's my C in. And then I probably the name 6 bits is wrong. What that really is the expected output of this for the sum, the expected sum output. Right. So what I'm doing now is if subtract is 0, so the adder is just adding, then my expected 6 bits output is just A in plus B in, right, as a standard logic vector. And my expected carry out is only 1. I set carry out to be 0 at the top there, my expected carry out. My expected carry out is only 1 if A in plus B in is greater than 15. Right, so all I'm doing in this instance with subtract 0 is adding A to B. And 1, 1, 1, 1 is 15. Right, so if the addition of A and B is bigger than 15, it's bigger than 4 bits. So my carry is going to be a 1. Right, and then, so that was A plus B. And then if subtract is not 0, so if subtract is 1, then the thing I'm looking for in 6 bits is A minus B, right? That's my expected output. Now look at what I had to do to find the expected. Let's go with that one. To find the expected output, right? So remember what's happening with B in. If subtract is 1, I'm forming the 2's complement of B in. So in arithmetically defining that is 15 minus B in plus 1, right? 15 is, as I said, 1, 1, 1, 1. If I subtract B in, that is going to be the 1's complement of B in. And if then I add 1, that's the 2's complement. So I'm adding the 2's complement of B into A in as my test case. And if that's greater than 15, then my expected output, but my expected carry out is 1. Okay, and then I'm going to wait for 1 nanosecond. All I've done so far is I've calculated what my expected output is. I've connected up the signals to the device that I'm making, or that I'm testing, and now I've got to check that its output's correct. Anybody got any idea why I've put this weight in here? Anas, you know?
I'm guessing because the processing time, you don't want to overload it.
It's not, well, so the right idea, the name I would use for devices is propagation delay. Okay, so the reason that is there, the reason that is there is to allow outputs to settle due to propagation delay. Even though we only talk about these things as ones and zeros and they happen instantly, they don't happen instantly. It takes a little while for the current to force the transistors to change state, inside each of the gates. So when there's a change on the input of the gate, the output of the gate doesn't change instantaneously. It's really quick, right? I'm only waiting for 1 nanosecond. Right? But it's not instant. In fact, that click probably took longer than a nanosecond. So maybe it is quick. Okay, so now the outputs are settled and I can do my tests. I'm going to check to see if S is equal to the lower 4 bits of 6 bits. And if it's not equal, I'm going to increment my errors. I could probably have put that after the assert statement, but I decided to do it separately. And notice I'm reporting exactly what values of A in and B in it didn't work for, if it didn't work. Right? So it makes, when you're testing 512 different possibilities, it makes 0 sense to not be able to identify precisely which possibility failed. So you have to identify in your report statement all the relevant information to say this instance failed. And I'll just scroll across and you can see the maybe, right? So I report the value of A in, B in and C in. And then I do the same thing for C out, and then we're done. Now that is more complicated than just cutting and pasting. I put it to you, it's probably about as complicated as cutting and pasting 512 times and changing each of the times. Right? At least here it's easier to see if there was an error, I think. So if there were 5 lines to test each instance in 512 instances, that's 2,560 lines of code to test if you just cut and paste. Here, I've forgotten what the number's in, but it's about 100 lines of code, right? It's 1/25th-ish of what you would do if you were cutting and pasting. Okay, it requires a bit more thought, but I think it's okay. Okay. Did I have that available?
So is that kind of like recursion? You have a loop inside of the loop? Is that
It's not recursive, so this is a nested loop,
oh, that's a loop.
right? That's what I would call these. Recursion is a bit different. Recursion is where it's a self-call. Now we haven't talked about it.
So you reach for one or desire destination.
Right, so if you have a function, right, and I'm just going to use pseudocode, right? So if you have a function x of n, and then if n equals 0, the first thing you need with recursion is a termination condition, right? So you need to stop the recursion somehow. Maybe we return 0, right? Else we return x of n minus 1, right? So that call there is the recursion. Right, it's a call, a self-call to the method we're in. Now you can do recursion. In VHDL, I don't think it'll actually get implemented. That's actually a really good, well, there's two good questions there. One of them is, can we do recursion? I suspect not, but let me check. But the other one is, it's possible to define functions in VHDL, and I should look at that. So I'll see about, don't know whether I'll put it in next week, but it's certainly something we should talk about. Okay. So, for your lab reports, one thing you should display is that this gets printed out. And just a screenshot of coordinate or of model sim with that as the output. That would be good with 0 errors or whatever you say there. The other thing you should include in your lab report is the whole test bench. Now, I can go either way. If code is only 3 or 4 lines, maybe 6 lines, include it in the body of your report. If code is like this, where it's over half a page, put it in an appendix. Okay? Include it, certainly, but only I don't. If it's in the body of the report, I find long code listings tend to get in the way of reading the report. Okay, let's see if we can go here, and I'll see if I can grab see if I can run that in quarters. See if I can download that. Now I don't know whether because of my not very performant laptop, whether I'm going to be, maybe I shouldn't have done that. Maybe I should start up the Citrix server, it might be faster to compile stuff. Yeah, why don't we do that? Okay. I'm going to take a 10-minute break, okay? And before we do that, does anybody have any questions about what I've talked about so far? It's about test benches. It's about converting between types. It's about forms so far. We'll just decide to start. Let me just. So let's take that break, and I'll be back. Let's make it 15 minutes. So let's back at 11, and that way I'll be able to get set up properly with the example. Oops. Huh. Okay. Let's just go. Work. Hmm. Okay, so let's start again. So what I've done is I've put the brought up quarters, and I think that is okay for our full adder. Let me just check. For some reason, I'm getting different versions on different places, and even my Dropbox seems to be completely devoid of the appropriate files, even though that's where I was working on it. So let's just check our full adder again. There's our full adder. That's the one I usually go to. Right, so it's A exclusive or B exclusive or C for the sum, and it's C in and A exclusive or B, or A and B. So that looks like it's right. When I opened this up, my C in was blank. There wasn't any calculation. So that's the full adder, and then the 4-bit adder. Look at that. That's why it's not. I'm running my tests, and there's nothing happening. And I'll show you the output of the test, right? So here's the test output, and let's just see right at the bottom. And I don't know whether I can make the font bigger. I don't think I figured out how to do this with this one. Here's view, bookmarks, maybe Windows? No. Okay, so maybe you can't read it back there, but it says test completed with 1024 errors. That means that every single test I did, the test for sum and the test for carry, 512 times, that means they all failed. And you can see all of that there. And even better, it says, and again you probably can't read it, that C out in that test failure case is undefined. And let's just have a look at the wave. Right, so there's the wave. The timing diagram, right? It's the inputs are all changing like you would expect. Right, they're all changing appropriately. But again, it's probably a bit hard to see. Down here, all the outputs are red. And you can see over here that they're all undefined. They're all U. And going back to quarters, you can see why now, because there's our architecture, right? It's completely bogus, completely empty. So there's nothing connecting my A, B, and C in to my S and C out. I'm just going to see if I have something different. No, that's what's there. That's really annoying. So if you don't mind, I'm going to leave it there. So the two things we need to do from now on is Lab 4, which you started last week, so that should be, the multi-sim part should be done, and you need to think about what I just showed you as far as the test bench is concerned, and get that working on your code.
What's all the errors?
Without all the errors.
Without?
Without all the errors. You need to test it, and it should end up with zeros. Mine's got 1,024 errors because there's nothing in my implementation for 4-bit adder. Right. What I'm going to do while you're working on your labs is I'll type it up. I don't want to. If you want, I can type it up live. I just don't know whether that's going to be very useful for you. I think you might be better off spending time getting the lab done. But can I just take a vote? Do you want to see me type it up live? I've got 2, 3. Oh, okay. Let's do that then. So what I'll try and do is I'll try and type it up live and talk my way through it, right? So here's our 4-bit adder, and just reminder, do I have let's just go there, see if we can pull up the blackboard rather than chopping and changing between Citrix and here. Okay. And 466 labs. Okay, so that's what we're trying to achieve. And let's just see if we can open that in a new tab. Okay, so first of all we need 4 of these things, 4 4-bit adders. Sorry, 4 full adders. And then we need to connect it up like that. So let's try and do that. One thing, so this is going to be our input, but then I need 3 temporary signals to connect each adder up to each previous adder. So let's see how we go about doing that. So there we are, we've got the component defined, it's a full adder. So let's do this. Let's call it full adder 0, and that's going to be a full adder. And then we need a port map. Right, and then I need to do that four times. And so there I have, and let me just see if I can make the text a bit bigger. I think that's tools, options, text editor, fonts. Let's make it 14 point. I think that's usually okay. Okay. Now, can I pull that out as a separate window? I don't know whether I can. Let's kill the IP catalog anyway. Detach window. There we go. There we go. That's a bit easier to read. Right, so there's the code. And I think that's the way you do an instance of the item. Let's just check that by going to our VHT. Right, and there's how the instance of the whole thing, the 4-bit adder is, right? Name of the instance, colon, entity, port map between the different signals and the entity's ports. Remember, it's signal to port. So these A, B, C, etc. are the signals, and these are the ports. Okay, So let's go back to the text editor. So now I've got to do some monkeying around with the map. Right? I've got to say, for the first full adder, what do I put into A, what do I put into B, and I think what I've got to do right, because it's the first three are the inputs, A, B and C in, so there's my I'm bringing in C in anyway. So on the first full adder, my C in, which is really this one, connects straight up to this full ladder. I've also got to connect it elsewhere, but I haven't got there yet. Now, elsewhere, there's a problem. I just connected B straight up to here. Right? That's wrong. But let's try it. So let's just keep going, and we'll do tests. Anybody ever heard of test-driven development? No? I've written my tests. I've got them, and now I'm going to try and make the actual thing that passes all the tests. So the next thing I need is connect S, right? So S out. Now, I have another slight problem, right? The carry out of the first full adder needs to go into a temporary variable so I can feed it into the carry in of the next full adder. So let's think about that. I think that means up here, before my begin statement, I need some temporary variables, right? And I'm going to call them signals. If I could type, it'd be wonderful. And I'm just going to, I could do these as std logic vectors. But I'm just going to do them separately. So I'm taking the C out of the first full adder and I'm putting it into the variable C0. Right? And then A1, B1, now C0, S1, and C1. Right, and then A2, B2, C1, S2, C2. And then let's just put that up there. Then A3, B3, C2, S3, and C out. Okay, so now what I've done so far is I've connected A to the A input, I've connected B straight to the B input. I haven't done these yet. And I've connected the outputs up in order, and I've connected the carry, the intermediate carries up in order. So let's see if that compiles. While I'm here, notice this summary page. total logic elements. Remember before I was talking about what the connectivity is, why it's all happening at once? This particular device has 6,272 logic elements. So far we've used 8 of them. Right, so we could probably almost make easily make an 8-bit CPU out of this device. Possibly even a 16-bit CPU. Just from the HDR. We haven't used any memory bits, and it's got 276 odd thousand bits, and it's got an embedded multiplier. So there's lots more we could do. That's why the project, I'm hoping that by the time you finish your project, this number is at least in the hundreds. It might be more, but I suspect it's only going to be in the hundreds. Okay, so that compiled. And now I think I want to see about restarting. And let's just see if we can clear this. No, that one. Let's run it. No, I still got the same number of errors. That's interesting. Wonder why I got the same number of errors. Did I get, let's have a look at the wave. Did I get any, I didn't get any difference in the wave. Let's just try this again. So let's re-simulate, just in case I got the, just in case it's still using the same data from before. So we re-simulate, we add those input and output signals to the wave, and then we bump that up. I put in a 1 microsecond delay, so we need at least 512 microseconds to run the full simulation. And I've forgotten where my log. What's it called? Toolbars? No. Transcript. Yeah, I'm still only getting U, and I'm still only getting undefined as my output. That's interesting. That should be okay. Let's just check the implementation of the full adder, and that's doing the right thing. So S and C out are the outputs, and I'm doing the exclusive OR of the 3 inputs for S. So they should be being defined. Let's go back here and check what's happening here. I'm wondering whether there's a problem with the way I've done my port map. It shouldn't be, because look, the A here is to the logic vector, and the A here is just still at logic. Signal to port. So what I could have done here,
That's what you had last class.
sorry,
You had a pointer to A last class.
sorry, I can't hear.
So last class when you did it, you had it pointing to A. So A parentheses 0 to A like that.
The other way around?
No, that's how you did it last class, I'm saying.
This, like this one, yeah, it is. I saw the example on that web page and I thought maybe we could shortcut it, but that's so let's try that and recompile again. So what I'm going to look for now is if that has any impact on the 0th bit output, right? No, I can't. For some reason, what's the error? 4-bit data cannot be indexed because it is still at logic U type rather than array type. I've got it the wrong way around. So maybe it is that way round. That's port to signal. B to, that one should be alright. S to S naught. And that should be the other way around, C out. Okay, let's try that. So one of the things I find with this class, and one of the reasons I'm okay with doing this for you live, is students get lots of red here and often give up a little too early. You will get lots of red, right? So just keep trying. Don't try too much. Like if you spend a whole day on it and it's still red, that's too long. If you get to a point where you've been at it for between half an hour and an hour and it's still red, stop and ask someone. Ask me. I'm always available on Discord. Just instant message me there, send me an email, whatever works. I may not reply instantly, but I'll reply as soon as I can. Just don't say my code is broken. That doesn't help me and it doesn't help you. Tell me something about cut and paste the error message and maybe the code or something. Just give me a bit more detail. Okay, so that ran. Let's resimulate and try again. Oh! No, sorry, I thought we had a change, but no, it's still... What I'm going to do is I'm just going to stop model sim completely, just in case there's something, and restart it. I've done my compilation. I think everything should be okay. Aha! Anybody notice what happened? No, that's expected. I just started up. Before, when I started up, it didn't have the full adder in this list. So even though Quartus had the full adder and I'd added it, for whatever reason, because when I started Model Sim, the full adder didn't exist, it wasn't in this work list. If the full adder is not in the work list, it can't be simulated. So I think, fingers crossed, I could still be wrong, but I think that's why the outputs were always undefined, because that full adder wasn't in the work list. Now, the thing I want to simulate is that 4-bit adder, and now, as Michael said, the things show up, right? And we can add those to a wave, and we can change our timing so that we get the whole simulation, and we hit run. And now look, I've got ones. Yes. And let's just have a look at the log. What was that called? I've forgotten what that was called. Where's the log? Processes, was it? No? Source? That's the source code. Sim? I thought there was a way, the thing I just killed. Library, objects, processes, wave. I can't find the log. The output for my, I killed it. I can't find the log. Before, when I killed it, it appeared in this list, didn't it? It's the wave. And model sim. So I want to see the output of the simulation, right? I want to see what the test says. Because I suspect now that we've run the test, I suspect our errors have gone from 1024 down to 512, right? Because it should now work for adding two 4-bit numbers, but it's not going to do anything different with for subtraction. Coverage, mode, process, profile. file, copy. I don't know what happened to it. For some reason, the log is no longer there. Let's just see if I can Google it. And it's about transcripts. I shouldn't have pulled the window out. See, that one just comes up whenever I redo the the wave. If I kill that, it'll come back again. If I add those to the wave again. Right, there again. Everything's still there. I'm at a loss. Any thoughts? It was there last time I killed it. Tools. TCL. Garbage collector.
Maybe you should update Windows.
Sorry?
Maybe you should update Windows.
Yeah, maybe I should update Windows. View. Maybe it's view. Transcript, maybe. Yeah, there we go. It's called a transcript. Sorry. Oh, look at that. You can't read it, but it says there are only 384 errors now. Okay? So, that's not too bad. But the reason there's still errors is because we haven't finished, right? So let's finish. So where's my code? There's my code. So the issue is I haven't done anything about forming the 2's complement of B. Right? So I need to, well, I have done something. I've added the I've added the carry into the first full adder. Okay, so what I need to do now though is I need another signal. I need to have B bar, right? And that's going to be a static logic vector, and it's got to be exactly the same size as B. Right, and then what I need to do is B bar of 0 is equal to B of 0 exclusive or Cn. Right, and B bar of 1, 2, and 3 is that. And it's now, probably B bar is the wrong name because it's not necessarily B bar. It could be, and let's keep it something a little bit more descriptive. So it's, let's call it processed B. And then instead of B here, I need processed B. And you'll notice I could have left, I was barking up the wrong tree when I changed FA0 to be the full mapping. This mapping worked fine. Otherwise I wouldn't have gone from 1024 errors down to 384 errors. So I could just do the same thing. So now my process B should be, remember what we're doing again? Right, this piece here is processed B. I'm taking my carry in and I'm forming the exclusive OR of that B input with carry in. And that's what's happening. Okay, now I can recompile it again. And just because I now no longer trust model sim at all, I'm going to kill it and restart it after I've compiled, just in case. I was a little perturbed that full adder component didn't show up. Okay, we've done that, so let's do a restart model sim. And there's our work, and we can simulate that one and add those ones, maybe add those ones to the wave so we can see the output. And then here we can change that to 600 microseconds. And then the view was the transcript view. Ah, we've still got errors. And we've got more errors now. 576 errors. That's kind of interesting. Anybody got any ideas? What happened?
Sorry, do you know? You know what happened?
I know exactly what happened. In fact, I think I've already set up Lab 6 to help let you figure out what's So, without any explanation, because I want to leave that for lab 6, it's related to what actually, a little bit of explanation. It's related to what I said earlier, right? That's, at least I think I know. Let's just, I had that happen when I was doing this. Like I said, I wish I'd kept the thing that actually worked. That's interesting. I thought it was because of that. I know when I first did this, I had 1 nanosecond there. And 1 nanosecond wasn't enough for the propagation delay so that the outputs had settled. So I'm a little confused now. Let's just do this. Love the way it goes clattering and banging like that. So there's the wave. Let's just check that the wave is there. Looks like it is. So it is still having a problem. Let's just go find the first problem it has. Oops. I should have cleared it before doing it so that we only had one run in there. So the sum isn't correct. For b equals 2. That's interesting. Let's have a look at our full bit adder. Oh look, cut and paste error. Right? So that's why the errors went from 376 up to over 512, because I wasn't processing B correctly. So even for C and 0, the full adders weren't getting the right numbers. Okay. So let's try that again. I'm not hopeful we're going to get down to 0 errors. It's just because it's been one of those days. But we'll see how we go. Okay. And just to, because I don't trust model sim, I'm going to restart it completely and see how we go. Let's just do our check to see that all the work products are there. They are, and we can simulate the test bench. And then we can add that stuff to the wave so we can see it. The wave doesn't really help much with such a large number of operations, right? I'm doing that more because I can rather than it being particularly useful. But anyway, it means we can look into it in a bit more detail. So there's 600 microseconds, and now let's have a look at the transcript. Oh no. Look at that. It worked. Finally. Test completed with 0 errors. Right. I didn't think that had happened. Anyway. Thank you. Okay, so your job, 2 jobs. One of them is to get Lab 4 done, which is basically that. The other one is to get Lab 5 done, which is to basically take Lab 3, deploy it to one of the boards, and take a picture or a couple of pictures of the half adder running on the board. Okay. Both of those need to be written up. I don't know whether the due dates are correct in Blackboard at the moment, but I'll give you plenty of time to do it because they're the first real ones. For Lab 5, I am going to expect a test bench in Lab 5. We probably won't have time today to do it in class, so I'll give you lab time next week to finish off Lab 5 and start Lab 6. Okay. Before we go do that though, let me just see if I can. There we go. Now see it? There we go. You probably can't see it. Let me just take a screenshot, and maybe if I can. I think there's only one in that lot there. So one of the problems with this that spike there, right? I don't know whether you can quite see it, but that line there should just keep going at logic 1. But instantaneously here, it drops and then goes up again. And the reason, it's called a glitch in digital logic. The reason is because of propagation delay, right? The inputs change, right? I'm going through all possible combinations of inputs. So this one changes between 0 and 1. all of the others change between 0 and 1. When this one changes, it potentially has an effect here, which potentially has an effect here, which potentially has an effect here, which potentially has an effect here. So you could think, okay, going from here to here, there might be 3 or 4 gate delays, right? There's going to be an exclusive OR. Inside here, there's going to be the longest delay is going to be an exclusive OR and an OR gate. Right? So add another gate, that's 4 gate delays from here to here. But from here to here, there's 3 gate delays, and then another 3, and then another 3, and then another 3. So the total delay here is about 12. Right? Because that change doesn't affect everything instantaneously, things get halfway. So that for a very, very small amount of time, the output is incorrect. Because I put that delay in there, my tests all pass. But just because your tests pass doesn't mean you're testing everything. And in digital logic, it's possible that if that thing goes to 0 and you're controlling some machine, that could kill someone. Right? So one of the things you've got to be very careful of when you start dealing with this sort of stuff is that you don't have any glitches. And I realise it's still a way away, but I believe Lab 6 is all about glitches. Right? And I think that picture, yeah, so you can see down, I don't know whether you can see from back there, but here there's a glitch in the pink one, there's a glitch in the green one, there's a glitch in the green one, and there's a glitch in the red one. Right, so there's another glitch in the pink one here, and there's another glitch in the pink one here. Right, so this one is, this lab 6 is aimed at taking what we've done so far and trying to remove those glitches. Okay, any questions? Okay, I've got about another hour and 15, so let's get those labs done. I will bring out the boards if you want to try and run Lab 5. And remember, you should already have done most of Lab 5. The only two things you need to do extra are, one, deploy it to the board. Some of you have already done that, but take pictures of that it's actually doing the right thing, right? So press the buttons and show that the right LEDs are on, or don't press the buttons and show that the right LEDs are on. And then the other thing you need to do is to put a test bench around the half adder for Lab 5. Okay, it's the same VHDL code you did in Lab 3, but now it's Lab 5, and you've got a test bench you've got to deploy it to. Okay, thank you. Let's get going with that. And feel free to take a break or what have you while we're doing this.
doing it.
It's just spend hours of every month.
that you should probably just do it. it'll come up with, you know, the HDL2, the HDL7, remember we say first time the HDL. Okay?
So then it's 0.
And then when the oil function change that software. No, right, settings general. And
Oh, okay.
you might be able to browse the one, but no, you have to default it. So you could say you can tell it before. Okay, that should be fine. That is correct. Oh, I see. Okay, so all I did there is I just right-clicked settings and files, and I added all I had to do was the files. I think that's all you need. Just check that I'm right. Okay. The only trouble with that is now you have to make sure that the path is the same. You can't move them around without changing the path. Okay? those lines 28, 29, and 30, you just put a double minus at the beginning of them to comment them out. And let's just see what happens. Right, so it's now reading 5, the same error. Yeah, I used to hit that button, and for whatever reason, it doesn't seem quite. So that controls everything. So here's, I'll just put line 28 back in and then bottom. No, it just doesn't.
It does the same thing, though.
Yeah, it didn't do all the. So go back.
I'm saying, I said, you mentioned something about this button.
And this is doing the right thing now. But for whatever reason, something changed. Just keep that one. Just one at a time. So. How did you change it back to yellow? What did you?
I said,
Don't just say. Okay, so here's a problem with that line. Position. So it's not an error, but one thing probably a little bit that happens. The HDL is non-facing, so it's okay. It's not the error. Aha. I thought it was something to do with so one thing you do want oh, wait a minute. Always I think I've seen you've got both of these lines at CE on C. Right? And don't think it should be like, but if we just change this one to C0. Right? Because remember, we don't want to carry in for a full out of 1. No. You divide it. Oh, see, just without the. Yeah, like that. Now just try and hold it now. Don't think that's the error, at least it doesn't make sense that that's the error. So now what I'm going to suggest is cut positional associations, copy positional associations. Copy, paste it into. I know there's. So just see. Okay, see what it says. So, in the association list, your named association same description, then all position loss. So that's sounding to me like we've got something in the wrong. Yes. Right. Here the order is A, B, C, C out. Right. So I think you swap, well,
How much like a swap?
like,
I mean, they both swap.
I think that's try well no because then you'll have to go into full ladder and fix it there as well. So just swap those two. The S and S. Well no, just line 20, just try line 20 for the last two. So take that. Let me just check mine. Did I get the I'm just checking the port map ordering again. A to A naught, B to B naught.
I noticed that for lines 26 to 28, you getting like have the same.
Right, I was trying to use the shorthand notation that I saw in the web page that I put up, just to see if it would work, and I got sidetracked. The reason I changed 125 to be like the way you have it was because I thought that might be the error. But I think now I can actually change line 25 back to number 3. So port map A to A out A0, B to process B0. Process B is a signal, still in logic records, read out to 0, that's correct. So that looks right.
Maybe the error is in line before. Say this because my S is before the signal. So maybe that might be the error.
Yeah, it's usually pretty good about the try swapping it over again. Because I think it should probably be swapped anyway. I'm just going to try see if that changes anything. Something about that order is normal. See, I thought that was the way it was supposed to signal on some of it. I don't know why the first one is not working out. No. That's really easy. So, you don't mind. Would you mind just emailing the copy to me, and I'll see if I can find out a rational explanation. Okay?
Sorry.
No, that's awesome. So in the meantime, so the labs look good this one?
That's it. I thought you would keep this until the end of semester. Okay. So just keep it at home. I'll have another one here if you need it. Okay. Okay. All right. Let me just take a swig. Yep. Right. Because settings, files, and you've got those two there. There's two things to do. One of them is that those files weren't in here, and they are in here, so that's a thing. The other thing is, again, device settings in general, your top level entity is a lab 4. So what it's looking for is a lab 4.exe.
Oh, okay.